Hello, everybody. My name is Pranay, and I'm a grade 11 student at St. Andrews College in Canada. I'd like to thank you all for attending this research symposium today. I'd like to give a little backstory as to why I chose this topic. For the last year or so, I've seen many videos on TikTok and Instagram showing people using autonomous vehicles in cities, and I wondered why they aren't where I live. I explored why and found that there is harsh weather in Canada that the autonomous vehicles simply couldn't handle. After figuring this out, I wanted to find a solution to bring these vehicles to where I live, especially after seeing the possible benefits. We've seen advances through motorized wheelchairs for seniors, but I noticed in my volunteering that seniors want independence and the ability to go wherever they please, but that really isn't the case with motorized wheelchairs. I wanted to see if seniors could just get into a car without having to rely on anyone using an autonomous vehicle. As a result, I evaluated three leading autonomous vehicle algorithms under harsh weather and then found ways to improve them. So, looking at the map on the right that you can see on the screen, research on autonomous vehicles is being done across the US. There's lots of research being done in harsh weather, as seen with the big red dot at the University of Michigan, which is one of the leading autonomous vehicle facilities. But although research is across the US, the miniature cars show where the cars are actually deployed. It's all in very good weather: San Francisco, Phoenix, Austin. My research studies the performance of autonomous vehicles in harsh weather because there's a higher chance of uh, crashes in rainy conditions and in snowy. My research studies it also because it's the biggest roadblock in their deployment across Canada. So let's look at how autonomous vehicles actually function. So there's a lot of technical components which help autonomous vehicles perceive the environment. And by the environment, I mean traffic objects like cars, pedestrians, traffic signs, lane markings, and even road surface conditions. There's a pipeline of technical components in autonomous vehicles that carry out specific tasks and interact with each other while driving. These components are perception, planning, and control related. As we can see in the model car, autonomous vehicles are equipped with high-quality cameras, LiDAR, radar, and ultrasonic sensors. The inputs from these sensors are fed to the perception components to assess the environment and vehicle state. Based on these inputs, prediction and planning tasks are carried out and eventually used by control components to generate motor commands. The perception component plays the most important role in the performance of autonomous vehicles in harsh weather conditions. The images taken from cameras are fed to computer algorithms to detect objects in the images. The object detector should be able to accurately classify traffic objects and locate those objects by drawing bounding boxes around them. So, let's look at what's the real problem here. Well, object detection models play the most important role in dealing with challenges of harsh weather. Simply, the function of these models are to classify objects in images and locate the objects inside of the image. As you can see with the diagram at the top, you start off with a normal image from a camera of a couple cars in front of you. Then you go through the backbone and the neck of the model, and you get to bounding boxes with the cars being classified as cars, people classified as people, and so on. Deep learning object detection holds great promise for advancing autonomous vehicles, but it requires training on robust datasets to handle the complexity of real-world driving scenarios. The quality, quantity, and diversity of the data used for training, validation, and testing directly impact the performance of deep learning models. You need to have a huge set of data that you gather to prep it and have the best model trained. In this research, I assessed the effectiveness of three deep learning models for object detection using the Canadian Adverse Driving Condition dataset. This is to establish a gap we need to bridge before autonomous vehicles can be deployed in harsh weather. The problem is that most standard datasets in the industry for autonomous vehicles are from normal weather conditions, and fail to cover harsh weather like snow, dense fog, or heavy rain. While there are a couple datasets gathered in the last 3 years in harsh weather, the volume is still fairly limited. Research and benchmarking on these datasets are still really primarily geared towards normal weather conditions. I hypothesized in my research that the industry-leading models that are trained on datasets from normal weather will not perform well in detecting objects in harsh weather. I also think that the detection accuracy should improve once these models are trained on harsh weather datasets. So let's look into my research methodology. So the goal of my research method was to create a more comprehensive evaluation of the three industry-leading deep learning models to assess the effectiveness of object detection tasks under harsh weather conditions. I selected the SSD, FastR CNN, and CenterNet models for the evaluation along with two datasets. The Kitty dataset that I used represents the industry standard used to train and evaluate object detection models in autonomous vehicles. And in the first steps of my experiment, I trained and evaluated the three models on the Kitty dataset to establish a benchmark accuracy. The second dataset was from harsh weather, for which I used the Canadian adverse driving condition dataset, and the annotation data format that the company used wasn't compatible with the training platform I used, so I had to manually annotate 370 images. In the second step of my experiment, I evaluated the models from step one, which were trained on normal weather, and evaluated them on harsh weather to see if the standard datasets are effective in detecting objects in harsh weather. This would be if we placed an autonomous vehicle in San Francisco in the snowy weather of Canada. In the third and final step, I trained and evaluated the three models on harsh weather to assess whether these models will improve in object detection accuracy when trained with the relevant dataset. I use the RoboFlow platform to pre-process the datasets and the TensorFlow platform to obtain the pre-trained object detection deep learning models for my training and evaluation steps. To visualize the training and evaluation results, I then employed a Google Colab notebook where I used Python code to bring this to life. The flowchart on the right shows basically summarizes my steps. So as I went deeper into the research, one of the challenges was to determine a metric on which I can evaluate the three models. There are a few standard metrics for object detection tasks like precision, recall, and losses, but the choice depends on the object detection task. For example, if I were to try and detect people wearing masks in a crowd, it doesn't get impacted by false negatives. And in that aspect, both precision and recall are important for autonomous vehicles, as we don't want to avoid an incorrect detection or a misdetection. That's why I chose the mean average precision, MAP, which considers both precision and recall. One of the biggest challenges I had was preparing the harsh weather dataset. As the dataset is not widely used in research, the labeling and annotation of this dataset wasn't available in formats compatible with research platforms. With the Kitty dataset from normal weather, it was available in COCO, Pascal VOC, and CSV formats, which can be used in the research platforms like TensorFlow or PyTorch. But the harsh weather dataset was not available in any of these formats. As a result, I had to manually hand annotate a subset of the most relevant images and use it for the research. Another valuable experience is that it takes time to learn the research platforms, as there is minimal to no documentation available pertaining to object detection tasks for autonomous vehicles. Also, the object detection area evolves at such a fast pace with frequent upgrades to research platforms that it causes incompatibility issues with current objects. In the middle of my research, for example, TensorFlow upgraded its version, which made my APIs incompatible, and I had to work with the TensorFlow team and the TensorFlow community to resolve this issue. Although it took many long hours for these difficulties to be surmounted, it was an amazing experience and it gave me great personal satisfaction to explore an area of such high interest in the research community and make my own contribution. So let's look at the results. All three models, as you can see in the bar graphs, have an amazingly low MAP score in scenario 2. That's where I performed the object detection evaluation on harsh weather using models trained in normal weather. This strongly indicates that the leading object detection models, primarily trained on datasets reflecting normal weather, prove ineffective in detecting objects in harsh weather. The harsh weather dataset is from harsh Canadian winter weather conditions, and I observed with many images that there are snowflakes, ice slurry, and they're all covering the camera's optical window, and it forms an opaque blockage on traffic objects. This can deteriorate the image intensity and obscure the edges of the pattern, which leads to detection failure. As we can see, the MAP showed a significant improvement in scenario 3 for each of the models, where I trained the model with the harsh weather data and then performed the evaluation. This improvement underscores the fundamental capability of CNN-based deep learning models, where it learns hierarchical representation of the features from the input data. By exposing the model to a diverse set of training data, the deep learning model learns to generalize its understanding of the underlying patterns, which develops the ability to make a model more accurate, and it makes better predictions on new unseen data. Among the three models, as we can see in the bar graphs, the CenterNet, or the bottom graph, performed the best in all three scenarios, including the harsh weather. This may be attributed to the anchor-free architecture of CenterNet, since it doesn't rely on predefined anchor boxes, and it directly predicts the properties of the bounding boxes, including center coordinates and dimensions. The results also show that models with one-stage architectures like CenterNet and SSD perform better than models with two-stage architectures like FastRCNN. This may indicate that processing an entire image in a single forward pass, eliminating the separate stages for region proposal, results in better localization for classification of objects in harsh weather conditions. The training and evaluation results from the Kitty dataset are the best for all three models by far, primarily driven by the dataset's volume and number of annotated objects. There were almost 7,500 images with approximately 52,000 annotated objects in the Kitty dataset, compared to the 370 images with 2.5 thousand hand-annotated objects in the harsh weather dataset. This discrepancy indicates that the object detection precision on harsh weather will improve with the increase of training datasets. The limited number of frames within the dataset from harsh weather is due to the highly tedious nature of hand annotating images, which needs to be fixed in the future. So let's wrap this up. In conclusion, we can tell that object detection models that are trained in normal weather are not sufficient and cannot be used for driving in harsh weather. This conclusion is completely in line with my hypothesis. As a path forward, here are my recommendations. We need to build more harsh weather datasets. As I found in my research that deep neural networks have the capability to detect objects in harsh conditions if trained with the relevant data, we just need more of these datasets. We also need to increase the use of driving simulation platforms like Carla and AirSim so that we have more accurate representations of harsh weather and testing on that harsh weather. And finally, we need to create the datasets in formats that are accessible to researchers. I wasn't able to use the harsh weather dataset, but I had to annotate it myself. As a key takeaway, I would say that we need better datasets with harsh weather to train autonomous vehicles and bring them to harsh weather like Canada's. Thank you for listening, and I would like to open the floor to questions.
Thank you, Pranay, for that great presentation. Any questions for Pranay from the audience? So while the audience thinks about their questions, Pranay, what do you think is the biggest hurdle to collecting a lot more information about adverse weather conditions? or data?
Uh, well, the biggest problem would be access to such harsh weather because the cameras and everything available sometimes have problems in harsh weather themselves. Like they can freeze at some points, and it's just pretty tedious in general to collect so much data. Some of these data sets even took like a couple weeks for it to entirely be done. So it's a bit hard to make these data sets in general.
Got it. Any other questions for Pranay? So I'll ask one more, which is obviously this is a highly technical project you undertook. What was the biggest challenge for you?
I'd say understanding how the models work was the hardest problem because I really want to know how the things I'm using work. So I spent probably a month just figuring out how each of these three models actually work, like their neck and their backbone, how everything works together. And I'd say that learning how these metrics work is also pretty hard.
Got it. And then one bonus question, do you plan to take this research further?
Well, I hope to maybe try again with a better data set once a data set like that would come out. Or I would look to maybe applying one of the CenterNet models since it worked the best in a robot. Since robotics is one of my passions, I would love to apply it.
Got it. Well, Pranay, thank you for the wonderful presentation about the terrific work you've done. And well, okay, there is a final question that came in from Ryan. If there are malfunctions from the cameras themselves, how can improving the image detection in cameras improve autonomous vehicles in harsh weather?
Well, these malfunctions are mainly in like supreme harsh weather. I'd say in like the minus 40 degrees Celsius standpoint. So in general, we're in the worst weather that we see, at least where I live, it's like minus 20. So these weather problems shouldn't be that bad. Only if we were to collect in like the most north parts of Canada would it really be a problem.
Got it. Well, thank you, Pranay, and thank you to Ryan for the great question.